So the next question, an adiabatic nozzle is having a steady flow of carbon dioxide at 1 megapascal and 500 degrees Celsius with a mass flow rate of 5,000 kilograms per hour and leaves at 100 kilopascals and 400 meters per second. The inlet area of the nozzle is 35 square centimeters. Determine the inlet velocity and the exit temperature. Okay, so let's get started. I'm just going to open it up on the other page. All right, there we go. So the first question is the inlet velocity. So let's just consult the conservation of mass, i.e. the equation of a mass flow rate, right? We have m dot equals rho a v. Now, what do we know? Well, we're told m dot, albeit in different units than what we want, but that's okay. Rho, are we given rho density? Not explicitly, but we are given the pressure and the temperature. For an ideal gas, that's all we really need to know to find rho. And A, we are given explicitly. So we have all the unknowns. We have everything we need to solve for the only unknown, which is V. So if we divide m dot by rho A, we get V. Now, m dot is going to be equal to 5,000 kilograms per hour divided by 3,600. So this gives us kilograms per second. Now, dividing by density. So how do we get the density? Well, we get it from the ideal gas law. We know that from the ideal gas law, density is pressure over RT. So the pressure at the inlet is 1,000 kilopascals. If we look at the tables, we'll find that R for carbon dioxide is 0.1889. That's kilojoules per kilogram Kelvin. And the temperature we're given is 500 Celsius. So we need to put that into Kelvin. And it becomes 773. So this expression gives us the density. And of course, we're multiplying by the area, which is given in centimeters squared. So we do have to divide by 100 squared to get into meters. So we end up with 35 times 10 to the negative 4 meters squared. And if you crunch all this, you'll get that the velocity is equal to 57.9 meters per second. Now, again, this is the velocity at the inlet. So whenever we calculate anything at a certain section, we have to make sure every piece of information we're using is at that section. So if they say the inlet, we're using the inlet pressure, the inlet temperature, the inlet density, the inlet area, all right? And if you do all that, you should get 57.9 meters per second. Now, the next part of the question asks us to find the temperature. So the way we can do this is we can appeal to the first law of thermodynamics, which of course we know by now is Q dot minus W dot equals, well, whatever type of energy we have. So in our case, we obviously, this is a steady flow device. We're going to use enthalpy. So we're going to have m dot H2 minus H1 plus, we have some kinetic energy, V2 squared over 2,000 minus V1 squared over 2,000. And the reason I'm dividing by 2,000 is to keep everything in terms of kilojoules, to keep it consistent, because generally that's what we express energy in is kilojoules, but you could do it either way, but keep in mind that you want to be consistent as always. Now, okay, well, where do we go from here in terms of temperature? Well, we're told that the nozzle is adiabatic, which means there is no heat transfer. Adiabatic definitionally means that Q dot is 0. Okay, well, it's a nozzle. There's no work ever being done in a nozzle. So clearly this guy is also 0. And the whole left-hand side is 0. Now, if we divide the entire equation by m dot, we're left with H2 minus H1 plus 1/2 of 1 over 2,000 of V2 squared minus V1 squared. And bringing that over, we have H1 minus H2 equals 1 over 2,000 V2 squared minus V1 squared. Now, V2 squared is told to us as 400 meters per second. V1 we just found over here. And all we're solving for now is this change in enthalpy. And how does this help us find the temperature? Because we know that the change in enthalpy is equal to Cp delta T. And if we plug in here into this equation, if we plug in V2 and V1, so 1 over 2,000 times V2 squared minus V1 squared, and then we take all of that and we substitute it in here, and then we divide it by Cp, we can get the delta T. And we know that delta T between T1 and T2, we know T1 is 773, and it's T2 that we're trying to find. And this is how we're going to find it. So anyways, to summarize, if we do this whole 1 over 2,000 times 400 squared minus 57.9 squared, which is this guy, divided by Cp for carbon dioxide, which is 1.126 kilojoules per kilogram Kelvin. This gives us 773 minus T2. And if we solve for T2, which is the exit temperature, which is what we're looking for, we will end up with 703.4 Kelvin.